Yeah, that's it. Okay, so you pick your best method, your theory, your basis set, all those things, run an opt and freak, and then you get the thermochemical values out. So let's look at this. So I said in your calculations you would report the G and the H for all of your molecules. And if you have a reacting system, then you need to report delta G and delta H. This is a very simple system. It's just the cis-trans isomerization reaction of dichloroethylene. And so here I've just defined the trans as the reactant, the cis as the product, and I do those two calculations. And down at the bottom, you'll see that we did the partition function and we talked about all those things and we compared that part. That was down there in the thermochemistry area. So in the thermochemistry area, you have these two lines: the sum of electronic and thermal enthalpies, so that's H, and then the sum of electronic and thermal free energies, and that's G. So this is H and this is G. So this is for the reactant and this is for the product. So now we could do delta H and delta G. So it's pretty straightforward. So we're looking at this. So the delta H is the product minus reactants. Morning. And so why are these numbers so extremely negative? Let's just review that. So all of the energies in Gaussian are negative. So if I tell you that there's a negative energy, in your mind, you should probably be thinking, well, what is zero energy? Why are we negative? Zero is your reference point. Okay. So for enthalpy of formation, what is the reference point for enthalpy of formation? By definition, we've said certain things have a zero enthalpy of formation, and then everything else is relative to those things. What are those things? It's not in the notes.
No, I know.
Okay. Yeah.
I downloaded my PowerPoint.
No, that's fine. I was just making sure that you weren't like spitting
there, like state of matter.
The state of matter is important. So solid, liquid, gas, and we don't want to necessarily define, because the different materials are different things. So we have sort of a vague definition of the state of mass. It's specific for each material, though. So we pick the state of the material at room temperature in 1 atmosphere. So that if it's like carbon, it's a solid. So then for carbon, the reference state would be solid. For oxygen, it would be gas, 1 atmosphere room temperature. But what is the species that are set to zero for enthalpy of formation? What are those? Don't overthink it. So we have a table with all the substances and their H of formation values. Which ones are zero? That's a review question. So like the enthalpy formation of water is minus 285, okay, kilojoules per mole. Relative to what? What is the word? Enthalpy of formation. What does that formation mean?
Like the elements.
Yeah, it's formed from what? It's formed from elements. Yeah, the elements. What elements? Hydrogen and oxygen. So if I look at the enthalpy of formation table and I find hydrogen gas, what's the delta H of formation for hydrogen gas? Zero. Yes. And oxygen gas? Zero, because oxygen is a pure element. Its standard state is gas, room temperature, 1 atmosphere. And so the elements in their standard states are the zero energy things. For our thermodynamic tables, our enthalpy and Gibbs energy of formation. Okay, not for Gaussian though. For Gaussian, we have a different reference point because we don't want to have to try to get Gaussian to understand what solid carbon is and gaseous oxygen and all of that stuff. So we try to get rid of all states of matter in Gaussian. It's much easier for Gaussian to just say, okay, what's the energy of the Coulombic charge of protons, or the nuclei, I'll say the nuclei and their electrons all separated to infinite space. Okay. So that even if I form a hydrogen atom, I got one proton and one electron coming together, that's going to be downhill. So 0 is up there where the nuclei and the electrons are all pulled apart. So there are no atoms, there are no molecules. So everything in nature is going to be negative energy. So even the simplest atom, hydrogen, a proton and electron come together and it drops down a half a Hartree. And these are units of Hartrees. Okay. Okay. And so an H atom, E is equal to minus 0.5 Hartree. And since we can solve for the hydrogen analytically, that's like a definitional amount. Okay. Now we could calculate how much energy it would take to pull that electron completely off of that proton in terms of kilojoules per mole. And now we would have a conversion from kilojoules to per moles per Hartree, and that's what this conversion is here. So this right here comes from this definition. We know how much energy it would take for a mole of hydrogens to lose all of their electrons, and it would be quite a bit, 2,625.5 kilojoules per mole to pull that half of Hartree energy away. Anyway, so I'm probably off in terms of my example by a factor of 2, but this is the conversion. So if we have this difference, products minus reactants, looks like a tiny little amount, okay? So notice how these numbers are the same except for these last 3 digits, okay? That's typical for some small reaction like this. So we end up, and so these are significant, right? Convert those to kilojoules per mole, and it's 0.297. So I just moved the decimal place, and it's now 297 kilojoules per mole, negative. And so this is exothermic, right? So when it flips, then it releases some heat. It's exothermic. Okay. Let's do the G value. Okay. It's not good. It's not plugged in. Okay. Okay, the G value. So we go down and get the G's. You see it's 771,906 minus 771,897. So even a smaller amount, it's still negative, so it's spontaneous in the forward direction of 24 joules per mole. Very tiny amount of energy. There's not much difference between these two molecules, but it is spontaneous in the forward direction. So if I have a bucket, which I do, like a 5-gallon drum of trans 1,2-dichloroethylene in the lab, it's spontaneous for it to flip. Okay. In fact, we could calculate with this delta G what the equilibrium constant would be, right? Minus 24 joules per mole divided by RT, change the sign, e to the x, and I get 1.01. So I should have a drum that's 50-50 between these two. You know, why is my DCE not a 50-50 mixture? Does anybody know? Because it's not anywhere close. I buy trans dichloroethylene, I can set it on the shelf, it doesn't turn into cis dichloroethylene. And Gaussian can be used to answer this question, which is what we're going to do next. What does it take for that chlorine to flip around to the other side? What? Yes. For that double bond to break, to go to the antibonding orbital and let it spin around, okay? So it's got to spin around that dihedral. So let's map that dihedral. Let's do a Gaussian calculation and map this around. And so with the Z matrix, we can find that dihedral and we can scan it and scan that dihedral and see what the energy barrier would be. What do you think, just with a rough, what do you think would be the highest energy structure? You know, this is a low energy structure. This is a low energy structure. Where would it be at its maximum? Just guess. Well, no, trans or cis are both low energy structures. Yeah, and they're close to the same energy. But on this scanning this dihedral, where would the maximum energy be? You think 90-degree dihedral? Yeah, so that's a prediction, right? So if you were doing this for your project, you could say, I'm going to do the cis-trans scan of this dihedral, and I expect the 90-degree will be the highest. Okay, so you kind of have a hypothesis, you go do the experiment, the calculation, and see what the results are. So this is also a valid option for one of your projects. So here's how we scan a dihedral. We have the Z matrix. You guys know how to make this now. And so we've calculated carbon 1, carbon 2 bonded to carbon 1 with the bond length, hydrogen 3 here bonded to carbon 1, okay, at an angle with carbon 2, so we define this angle right here, okay. Chlorine bonded to 1, so this is atom number 4 bonded to 1, angle with 2, so we define that angle there, and then we have this dihedral with 3. So this is the axis for this dihedral, and it's 180 degrees, right? It's on the opposite side, so around these two planes. So you've got this plane here is one plane, this is the other plane, and the angle between those two planes is 180 degrees. Does everybody understand the left side of the molecule? I went pretty fast, okay? Now let's define the other side of the molecule. So we have the other chlorine bonded to 2, angle with 1, got that, and then dihedral with 3. So this dihedral with 3, so here's the 1, 2, 3 plane, here's the 1, 2, 5 plane. That's the one we're going to scan, okay? And then this is really key. I want number 6 to be defined relative to 5, not relative to anything on the other side of the molecule. You have to break the sides of the molecule completely, so that only one dihedral can flip that one side of the molecule. So I have to define number 6 relative to number 5. This is the really important piece here. This is the one we're going to scan, but this one right here defines atom 6 relative to atom 5, okay? And it's going to be 180 degrees because it's going to be on the opposite side of that carbon from atom 5, okay? But notice here, D2, we start out at 0, so 0 with respect to 3, so it's in the trans position, and we're going to crank it along, and it's going to go through 90 degrees and all the way over to the cis position. So I'm going to go 180 degrees with 10-degree steps. And Gaussian, this is a small molecule, it just chug, chug, chug. It only takes like a few seconds. I mean, maybe 2 minutes, to do this calculation. It's just called a static scan because all of the other bond lengths and angles are fixed. So we're just changing the dihedral, and we can see that dihedral scan over here. Look at this beautiful thing. So the energy goes up. Here's 90 degrees right here. So we're off a little bit. It went up again one more step, and then it dropped down. Now, I think if you came back the other way, it would do the same thing and drop down. So this really is the maximum. But this is a rough plot because, let me erase all of these because I've got a video. Okay. This is fun. Okay. So you see up here, so it's called a static scan because all the other variables are fixed. And then we can calculate that barrier. So look at this barrier. So we come across here, and it's 0.99. Or it's minus 997.62, and this is 0.78. So you see we have the barrier, 0.62 minus a negative 0.78, so that's 0.16 Hartree. Huge amount. Doesn't look like a big number, 0.16, but when you multiply it by 2,000, it's a 420 kilojoule per mole barrier. So what's the Arrhenius equation is essentially the Boltzmann distribution. At room temperature, how many molecules are able to go over that barrier? So you can treat it as a two-level system, right? So that transition state is the barrier. What's the equilibrium constant of molecules being at the transition state relative to the ground state? It's this, 2 times 10 to the negative 32. So that's how many molecules are at the transition state relative to the trans ground state at room temperature. So that's why if I start with a bucket of trans 1,2-dichloroethylene, there's only a chance of 10 to the minus 32 that there'll be a molecule at the excited transition state to go over to be the cis version. So even though it's thermodynamically favorable, it's not kinetically favorable. And so these transition states are how we determine kinetics with the Arrhenius equation. If you look at the Arrhenius equation, it's a Boltzmann distribution, using the transition state as the excited state and the ground state of the reactants as the ground state. So the sharp nature of this transition state is because we're using a static scan. We're not allowing any of the other bond lengths and angles to change, but they would change, right? If we're going to go from this to 90 degrees, we would have to break that double bond, so the carbon-carbon bond would stretch naturally, and the angles would change. Now we're in an anti-bonding orbital, and so there would be a change to the bond lengths of the carbon-hydrogen, the carbon-chlorine, and so on. So I tried to do a relaxed potential energy surface scan, and we'll see. It's kind of interesting. Okay, so here's the scan in action. Also, when you do a scan calculation, you get an output that gives you the angles and the energies, and so you can plot that yourself in Excel. So you don't have to just like screenshot this. I mean, that's nice. You can do a little snip and screenshot it like I did, but you could also take this little output of that dihedral and put it into Excel and plot it and make it look pretty. Okay, so that's always fun too. So let's look at this video. And so you can see that it's going from trans to cis, and then I step through it and look down here. You can see the energy. So right there is the 90 degree, and then it goes up, and then it starts to drop back down. Isn't that fun? I love Gaussian. Right? And you can go backwards and forwards using the little up and down arrows on there.
Okay. Or in a situation whereby you have a molecule where the highest energy is linear, like a straight line, instead of.
Let me see. What are you talking about?
So,
Here?
yeah. Instead of just the transition state is linear. Like
You mean it should be like this right here where it's smooth?
something like that.
Yeah, right, where it has a zero slope right here. Yeah, it's a critical point, a zero slope on that. And that's what I'm saying. It's sharp. It's sharp because we're using a static scan. Yeah. And because we're coming from one direction, and Gaussian's calculating the energies using the initial wave functions and then calculating the new wave functions based on the initial results. And so it's changing the cloud ever so slightly. So it kind of overshoots the 90 degree thing. But after a while, it says, well, this is too much energy, so it drops down to here. So this sharp thing, if we were to come this direction, I predict that it would go past 90 degrees one point this way and then drop down. And so that we would say that, the structure between those 2 points would be the 90 degree point. So this static scan is pretty solid. It'll work frequently. It'll work when the other relaxed scans don't work. And so I tried a relaxed scan, okay, where I let it would move to a point and then it would relax all the bond lengths and angles, and then move to another point and relax all the bond lengths and angles, okay. And it didn't, well, it may have worked, but it wasn't exactly what we expect, okay. We expect this nice, smooth transition where 90 degrees is the high energy point. But if I build this molecule with that chlorine at 90 degrees and the hydrogen pointing down, it may not want to stay there. It may relax and go all kinds of different ways. And look at what happens to this molecule. Okay. So I'm just showing you the dihedral at 90 degrees, and then I'm going to cycle through. Look at that hydrogen. The hydrogen really wants to be in the plane of the carbons, and then that chlorine moves over between the two carbons. So now we'll turn it sideways and I'll cycle through it again. Watch what happens to the chlorine. It actually gets so far away from the carbon that it says it's not even bonded anymore. Okay. It looks kind of like an epoxide, but with a chlorine instead of an oxygen. It's right above those two carbons, making a triangle. Okay. Now it's saying that that's the transition state. Okay. And so I guess, we could explore this. It might be interesting. The chlorine, it looks like the chlorine may go over the double bond and the hydrogen move in the plane around to the other side. So not a rigid rotation, but let me do it this way. The chlorine moves up over the double bond and the hydrogen moves in this plane like that. And then the chlorine moves down to the other side. So the hydrogen and the chlorine have two different paths. The chlorine goes over and stays in that above the carbon atom, and the hydrogen just slides around in that plane. Now, the one thing that I would caution our conclusions with, I would be cautious with, is this is with the 6-31G with the polarization functions on carbon only. Okay, what if we added polarization functions on hydrogen? We'd want to give that basis set, that electron, more freedom. And so anytime you're trying to do a calculation like this and you get unexpected results, expand the basis set and see if it's a real effect or if it's just an artifact of the smaller basis set. We don't have time for that, but if this was your research, you would not want to spend all your time studying this system extensively without changing the basis set. Do the same calculation with an expanded basis set and see if it looks the same. If it does, then you know it's not an effect of the basis set. This makes sense, because the basis set is what gives the electron cloud the most freedom. So if you get an unexpected result, expand that electron cloud and make sure that that really is a valley that chlorine atom's going through, and not an artificial valley of just the mathematics of where the electrons can be. Does that make sense? Okay. Also, the nice thing from the relaxed scans, you put in the product structure, a reactant structure, and a guess at the transition state structure, and you get what you gave it here for the product, for the reactant, and then this is the optimized structure for the transition state. And so you can look in here, what is the 1,4 bond distance? Okay, you can find it right here. It started out at 1.7 in the product and reactants, but then in the transition state, it's over 2 angstroms. Okay, so that's why it dropped the little stick on there. There's a range of values at which GaussView will say it's a bond, a single bond, double bond, or some in between. Okay, and the same thing with the hydrogen, the 1 and 3. It's a little different. Well, it's not that different. 1.09 versus 1.08. Okay, this chlorine still looks the same as the reactants and products and so on. You can look at the angles, and they're all over the place. But we do have a different energy. It was minus 0.62, now it's minus 0.64. So we have brought the energy of the transition state down a little bit by relaxing all the other parameters. So let's calculate it. Now it's, instead of 420 kilojoules per mole, it's 368. But so our equilibrium constant, or our activation energy barrier, is dropped to 10 to the minus 28 instead of 10 to the minus 32. Okay, so sometimes it's helpful to modify or to be able to start and stop calculations using Gaussian without GaussView. So this is the Gaussian window. Okay, you go in here, File, Open, and you get this section, or File New, you get this section. And here's what I was showing on the board at one time. I was showing the percent section, or I called it the percent card, or the root section, the root card. That percent and root sections have to start with certain characters. So it starts with the percent sign or the pound sign, or hashtag as we call it now. And so then you have the molecule specification section here, and we'll do charge of multiplicity. Okay, so let's just do a simple molecule like we did in class for hydrogen peroxide. Okay, so a simple Z matrix, start with the oxygen. Again, oxygen 2 bonded to 1 with the distance, hydrogen atom 3 bonded to 1 with the distance, angle with 2 with an angle, and so on, and then this dihedral. Okay. And so if we wanted to do an opt and freak, we have opt here, and then we have to add an additional step for the frequency calculation. So to do that, you see up in this button here, we have the additional steps. And so we would click that additional step button, and we get a really weird Gaussian. I mean, I don't know. They put a lot of effort on the back side, the front side, not so much. You click on that additional step, and you get this thing, which the screen is even like cutting off the menu. It's been that way for over a decade. Yeah. And so on multiple different machines. And so it's not my machine, it's not my laptop or whatever desktop. But anyway, but you can kind of see the menu items there. And so then you would click step and add step. So when you click add step, then you get this new, see, additional step, 1 of 1. And so we have an empty root card. It populated the checkpoint file here. And so this is what we would type in. The main thing being this right here, geom equals check. Okay. The reason that's important is the first step was the geometry optimization. Okay, so it optimized the geometry. We don't know what that geometry is for the second step. So we got to pull it out of the checkpoint file. So all your subsequent steps, you use geom equals check. It'll say, go get the geometry from the checkpoint file. That way you don't have to put it down here in the molecular specification section. You do have to put the charge of multiplicity though, because maybe you want to change that. So like maybe you could have it go from a singlet to a triplet or something like that. Okay. So there's also for each of these steps, this check mark button here, you can click that and you get this little screen. It doesn't submit the job fully, but it submits the root card, and then you get all of this business here. This is these are all the subroutines for Gaussian. It's called the link list. And I'll just put in parentheses subroutines. And if your root card has a major error in it, maybe you misspelled, instead of 6-31G, you just had 6-3G, which isn't a basis set, it will fail right there and say, sorry, you don't have, you've got an error in your root card. And so then you don't hit submit and leave and then come back and your calculation never started. So this is a way to check that root card to make sure it's a valid one, that you haven't made any gross typos. Okay. Then you can, after checking your root cards, you can go and hit file save as, and I like to save all steps to one file, and you give it the file name .gjf, and then you can run the job. Okay. So the run the job is the run button. So you hit the run button and it goes. So here's what it looks like while it's running. When you submit a job from GaussView, you'll see this window pop up and you see the things going at the bottom. And you can kind of check things and check the progress and so on. Now there are some important buttons on this screen. So the pause button does work. Okay. So if you're doing a big spreadsheet or something else on that computer while it's running Gaussian in the background and everything's really sluggish, and you just say, look, I'm going to pause the Gaussian calculation for a few minutes while I finish this task that's using up computer resources, and then you come back and you can unpause it. So the pause button is great. You can also pause after this subroutine. So if you're worried about it glitching, and you hit like a hard pause and it screws something up, you can pause it after the subroutine. So it'll go along, it finishes that particular link, and then it pauses. Then your computer or CPU resources and everything are restored so that you can do whatever other tasks you have. This was really important when you had one CPU with one core. Okay, and it's trying to multitask. Now, some of our CPUs have like 16 cores and so on. So Gaussian will be wearing out a couple of cores, and then you can work on the other cores and not even know that anything's happening. So it's not as important today as it was in the past, but anyway, those buttons are important. This stop button will kill the job. So if you hit that, let's say it's taking way too long and you're trying to get lecture ready for class and you thought it was going to be a fast calculation and it's going for 5 minutes and you're like, nah, forget it. I'm going to try something that's faster. You can kill the job, go back, change your basis set, change your level of theory or something like that and make it faster. Okay, once you're done, so this is joy when you see this right here. There's a quote at the end of every calculation, all right? There's some pretty funny quotes, okay? So this right here. You Never Know When You're Making a Memory by Ricky Lee Jones. Who knows? There you go. There's some great quotes. Some of them are quite long, okay? And it's always been there. I've enjoyed it. There's some really good ones. There's some limericks, okay? There's some great stories. But it's nice because sometimes you remember the quote and you're like, can't find that file. And so you could search for things in the quote to find that file. Or if I say, is this calculation the same as this one? You can look. If they have different quotes, you know it's a different calculation. Okay, so anyway, the quote has come in handy. If you come up here and hit this little document with the magnifying glass and like inspect the document, and that will open the output file. So here's our Gaussian output file. It starts out with some, again, information about who wrote it. And so let's do a tour of the Gaussian output file. So we have the link list. It's inserted after the root card. So these are what I said before. These are all your subroutines. So I don't understand it, but some of these things, if you wrote the software or you know about the subroutines, that might be helpful to you. It has the checkpoint file name. It has the root card, and then it has all of the link list, and then you get your title, and then your charge and multiplicity, and then the molecule specification section. Okay, so those are all of the different pieces. Okay, and so that's how they're displayed in the output file. Then you zoom down, you see the Z matrix. So the input parameters are summarized. So here's the Z matrix that you submitted. You can see your angles and everything like that. And then it takes all of this information, and this is nice. It gives you your bond lengths in terms of your atoms. It tells you what's paired, it tells you the angles, it tells you the dihedral, and this is the input values. Okay. It takes that same information and computes the Cartesian coordinates. So if you ever needed to get the Cartesian coordinates for whatever reason for this molecule, you could input the Z matrix and get the Cartesian coordinates. Okay. The point group is also computed. And so this is pretty neat. If you build the molecule correctly in terms of symmetry, then it will give you the point group. And the way we built this hydrogen peroxide molecule with the dihedral is that it's a C2 molecule. So it actually looks like this. Where it has a C2 axis down the middle of the molecule. And that's it. There's no reflection planes. The only thing it has is that C2 axis and the identity operator. So it's a C2 molecule. And then it has this thing called standard orientation. So the standard orientation, it takes your molecule and orients it like I've drawn it here, where the origin is the center of mass, and you have the X, Y, and Z coordinates, and it puts it in A, B, C order, where you have the rotational constants, A, B, and C, the three rotational constants, in this order where A is the largest, B is the intermediate, and C is the smallest. Okay. So what's the smallest rotational constant? Rotational constant is inversely proportional to moment of inertia. So if you have big masses spinning around the nucleus, that's a big moment of inertia. That means that's a small rotational constant. Okay, so the smaller rotational constants in this order are B and C. And so this one would be like let's say that's C. Rotating around this way would also move those oxygens. So that might be B, and this one is A. How do I know that? Well, because the oxygens really aren't moving. It's the hydrogens moving around the oxygens. And so that's going to be the smallest mass. That's in the denominator of the rotational constant. So that would be the largest rotational constant. So it sets up the standard orientation so that this relationship is valid. Okay. If we want to find the internal energy of the molecule, we could search for this SCF done line. So you see here, SCF done. It does the positions of the nuclei, calculates the electron cloud, it calculates the energy of the molecule at that geometry, and when it's done with that calculation, it says SCF. So SCF is self-consistent field. So as a field of the nuclei, field of the electrons, it iterates through this to where there's no changes with iteration. So it's a self-consistent field, energy, and and this is the energy. You can find that if you open the output file and you hit Control F, you can search for SCF done. Okay. Now, if we want to get the energy for all of those iterations, if you're tracking a long calculation and you want to know how long, how close is this thing to optimizing? So you've put a big molecule in, takes a week, 2 weeks. You want to see how many steps it's done. But you don't want to screw up the calculation. So you can copy the output file. So you go in and copy the output file, paste it into that folder. Then you open a command line terminal. So you go to the Windows button and you start typing in CMD. This pops up, terminal, you hit that. And so you've got this terminal window, okay? And so then you navigate to the directory where the output file is. So I want to go back, like from my user directory, I want to go back to the previous directory. I can take CD, change directory, ... and it goes back one. Goes to that one. So now I'm in the user directory. CD ... takes you back to the C drive. Then I go into the Gaussian 16 folder, and then I change directory into the Scratch folder. So now I'm where my calculation inputs and outputs are. Okay, so that's where I'm at in terms of the computer hard drives. And then I'd use the find command. Let me erase all of these because it's going to update. I use the find command, which is just like Control F in the file, but it searches through that file. So I type find space. Since this has a space in it, I need to put my quotes. So I put open quote, SCF space done, colon, close quote. So it's looking for this, and then I type in this file name. Now that's a ridiculously long file name. So I type in H2O, and I type in tab. The tab button will try to autofill everything else. And it'll autofill it out probably to the CHK file. So then I just backspace the CHK and type in LOG. So I've only had to type 6 characters. H2O, tab, through the CHK, I back up and type in log, hit enter, and this is what I get. It's beautiful. So this is telling me that the calculation is going pretty well. So if you've got a long calculation, and look at where the energy is changing. So here it's changing in the second decimal place. That's pretty high energy. Remember, each one of those, this is 2,000 kilojoules. Okay. Then it starts changing in the fourth decimal place. Okay, to right there. Okay, now it's changing. What is that? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. The 8th decimal place. Yeah. So it's getting close. When it, it's going down to find the bottom of the well. So the changes now are really tiny. And so we know that this calculation is getting close to finishing. In fact, it is finished. It's done. But you can see how close the job is getting to its lowest energy by seeing where those are changing. You could plot this. This would be the energy that it's doing while it's optimizing the geometry. Okay. Vibrational frequencies, IR intensities. This really isn't this course. This is a thermodynamics course, but for the spectroscopy course, this would really be super useful. And so you guys that did this in spectroscopy, where you're going into the Excel and you're going into the file and you're grabbing this number, hitting Control C, and then going to Excel and hitting Control V. Then you go get this number, hit Control C. Then you go into Excel, hit Control V, and you do this 3n minus 6 times if you don't make any mistakes. Okay, so this is a way to do this. So you can see this is just continuing what we've done. We could say find, and then in quotes, frequencies. So we find the piece that we're looking for. So I'm just finding this right here in the output file. Okay, I hit enter, and look what it does. It just starts listing the frequencies. So it lists every line where the word frequencies dash is. So this is really helpful to know a little bit about the MS-DOS, and this is the command line prompts, but it uses a lot of features like MS-DOS, like find. We could do the same thing with IR intensities, Raman activities, and we could pull all of those pieces, easy to paste into Excel. Okay, so it's a great way to extract the vibrational frequencies and so on, because they're very tedious to extract by hand. Now, work smarter, not harder. the command line and MS-DOS back in the day allows what we call piping or redirection. And so this, when we were doing these commands, notice where the output was. I typed this command and it sent the output to the monitor. Okay, that's great, but it's not really easy to cut and paste out of the monitor. Some programs allow it. I don't think command line does, but it'd be nice if I could send that output instead of to the monitor, send it to a file. So that's what redirection is. Instead of sending it to my face, send it to a file. Okay, so this is what these things are here. These greater than symbols are redirects. And so I'm saying find this, pound sign with a space. That would be the root card section. And then these are variables. This %1 and %2 are file name placeholders. So it's saying find this string in file 1, and instead of sending it to the screen, stick it in file 2. And so this is the convention. These REMs are just remarks for the user. Okay, so I'm saying this is how you use this program. You would type in parse.bat, then file name 1, then file name 2, and hit enter. So that's what you would do on the command line, and it would run this program. It would also find the frequencies in file 1 and stick them in file 2. It would find Raman activities in file 1 and stick them in file 2. And so you can create this little executable script. So if you're trying to pull information out of your Gaussian files, you can build your own little script and it'll suck all that information out. And then it's much easier to copy and paste everything and put it in Excel. The echo off just means it won't be sent to the screen at all. You could leave echo on and you could see it do all of that on the screen, and it would also send it to the file. So it would do both. Yes?
The question is, calculating the delta G and the delta G of the molecule, are we to build the reactants separately and the products separately? So
Yes. Yes.
I thought you can do it this way, like if you just grab the log file of the reactant,
Okay.
then you stick it to the test file. Can we run the calculations still independently while done running without stopping? I don't know if you understand. Like once I'm done doing the reactants, instead of extracting the file, then starting the job again. So can I just get out the thing I need from the reactant, then stick it to another test file, then start the.
Yeah, it depends on what reaction you're doing, but that's essentially what I did with the cis and trans, right? I optimized the trans molecule, and then I had the optimized bond lengths for the carbon-chlorine bond, the carbon-hydrogen bond, the carbon-carbon bonds, right, and the angles. And so then I just changed the dihedral, but I didn't start over building the cis version. I used the optimized bond lengths and angles from the trans version to make the cis version. Is that kind of what you're talking about? Yeah, it saves some time on the calculation because the hydrogen lengths and the angles have all been optimized. The only thing you're changing is maybe just the reactant and product pieces. Yeah, it makes it faster. Yes. Yeah. The nice thing too is you can look for not just the input file. You could put star.log and get every file that has a .log ending, and it will do it for everything in that folder. And then you could get all of your like if you're doing the enthalpy, free energy, you can put those search terms in there, and it'll pull it from the reactant file. It'll pull it from the product file, and it will label those based on the file names. So I'll show you that in a second. Okay, and then this last line opens Notepad, opens file number 2 in the Notepad. Okay, so you see when I run this find frequencies on this, it gives me the file that this information came from. So here's how we would use the parse thing. We parse.bat, and this is % number 1, file name number 1, this is % number 2. And then this is what we get when it comes out. Okay, so this is the syntax and this is the result. So it gives you the file name where the information came from. And so I searched for the root cards just so I would know what those calculations were. It gives me this, file name. Here's the frequencies. Here's the file name for the Raman activities. Here's the file name for the IR intensities. I went ahead and searched for CPU job time just because I wanted to see like a record of how long the calculations took. And then I looked to see if it was normal termination. That's a nice thing to see in case there was an error in the file. You don't want to use the results from a file that didn't finish correctly. Okay. So let's display now the molecular orbitals. You may want to do a project where you look at the molecular orbitals. So if you got your molecule, you load the checkpoint file. That's the important piece here. You have to load the checkpoint file, go to the MO editor, so Tool, MOs, and you get this view here. It's by definition has the HOMO and LUMO selected. So come down here and pick the Visualize tab, the Visualize tab. You can pick an ISO value. You can add these lists here, 1 through whatever it was, and you can put those numbers down here. It's just doing the alpha electrons in 9 and 10 and hit update. And when you hit update, then you have these little check boxes by your orbitals. And whichever one you check is the one that's being displayed. It's that simple. Open the checkpoint file, tools, MOs, visualize the ones you want, and then you can check them. So this is the LUMO. No, this is the HOMO, the highest occupied molecular orbital, and this is the LUMO. And I can't really say much about. I don't have any information out of these, but you can say, it looks like p orbitals on the oxygens interacting with the hydrogens, and then this, I don't know what to make of that, but maybe you find something interesting with your molecular orbitals, maybe for the catalysis, or something like that. Maybe there's something useful there, but that's how you do it. This MO editor is great in GaussView. Okay, we're out of time, but I did want to, show you just that command prompt. Yes.
Before you setting up the calculation, there's a part that says the keywords. Putting up the keywords on the Gaussian view.
Yeah.
Gaussian view. So if the keyword are not specified, the calculation will not proceed.
Right. Mm-hmm.
But I think the last time you showed us, you just set it up without putting up the keyword. It's Ross.
I don't know. You have to find out what you're, find out more information and send me an email with that. Yeah, so I don't. So I wanted to do that parse.bat on everything. It's going to be big. Okay. Oh, I didn't do the second file name. Okay. So I'm doing it on every log file in my Scratch directory, and I'm going to put it in output.txt. So it's running, and here it is. So the reason I did that is because now you can see it has all of the root cards of everything. So that's every calculation I've done. And I've got the type of calculation, everyone in that folder. I can scroll down here. If it was a frequency calculation, I have all of the frequencies for all of those molecules all in one file. I have all of their intensities. Like some of these weren't frequency calculations, okay? So they don't have anything. So here's, here's all of the Raman activities, IR intensities. But I just wanted to show you, isn't it nicely organized? It tells you the file name and where it came from, and then it tells you, the information that you're looking for. You could do this with your enthalpies and your Gibbs energies and have everything in one file, and then you can bring it into Excel and plot it or whatever you want to do your deltas calculations and so on. So that's really nice. So you can use that in general using wildcards like star.log. Okay. I could have used wildcard like H2O2 star.log. So it has to start with H2O2. It can have anything in the middle, and it has to end with .log. So, okay, that's enough.